Um, good afternoon. My name's Ian Wells. I'm from Cisco, and I'm here with my colleagues Ajay Simha from Red Hat and Vinay Rao, also from Cisco, and we're going to talk to you about turbocharging clouds for NFV workloads. So there's a big difference between an enterprise workload that you're usually using with clouds and an NFV workload. An enterprise workload, you talk to a service. There's a service running in the cloud. You say, I'd like to talk to this service. Even when you're using microservices, I would like to talk to this service. It tells you things, and you get it. You get back your data. You get back big lumps of data in big packets. Telco workloads are a little bit different. We're often in the flow of traffic, and that means that what we're seeing is iMix traffic, small packets, 300-byte packets, not 1,500-byte packets, and 5 times as many of them. We're looking at enormous bandwidth because we're looking at tens and even hundreds of gigabits of traffic coming from lots of customers across the internet. And we're looking at many, many flows going on at the same time. Thousands of customers talking to thousands of endpoints, millions of flows all going on at the same time. So it tends to work out very, very badly for networking in clouds.
So that kind of drove the main need for NFV. We have two things which are very important. One was performance. The other one is HA. So today we are talking about performance. So because of this, when you looked at traditional workloads for enterprise, a VirtIO as the forwarding mechanism is plenty good for that. You can get almost up to a gig throughput for per node, right? So that is plenty. So that was where we started off a long time ago when people started experimenting. That was no longer enough for workloads such as like a packet gateway where you need to terminate, say, 15 million subscribers, right? So then the next thing that people started using in NFV was to use PCI Passthrough, where you take like a 10 gig port and make the entire 10 gig port available to the VM, right? The one problem with this is, as you can see, there are two VNFs, VNF1 and VNF2. Because it's like a PCI pass-through, the entire NIC, physical NIC is available to VNF1, and VNF2 does not have a place to share that NIC. That is the fundamental problem with PCI pass-through. So the next thing that came along in the technology was SROV, which elegantly solved that by breaking up the physical 10 gig NIC into physical function, PF, and n number of virtual functions, VFs, right? So that the VNF could then, the VNICs could bind to a VF or one or more VFs depending on how many ports they had and what requirements they had. So here you can see SROV has solved that problem. Both VNF1 and VNF2 have been able to share that physical NIC and the 10 gig bandwidth. SROV presents one problem, just like there's no such silver bullet which solves all problems. So SROV, while it solved the throughput problem and sharing the bandwidth of the physical NIC, the problem with this is that the physical NIC drivers have to be, like the VNFs have to be aware of that. So whoever produces these VNFs, the NEPs, the network equipment providers, will have to constantly keep updating the drivers for these NIC drivers, right? So that is the problem. And then came along OVS DPDK, which kind of solves that problem by decoupling that and moving the basically from the kernel networking, it moves the networking into the user space and uses things like vhost user and other optimization which solves that. The DPDK also is it's very dependent on tuning, and if you want more throughput, you will need to dedicate more CPU cores because it's based on poll mode drivers. So that is kind of like the inherent, it's not an issue, but that's what we have to live with for DPDK, right? And then comes along virtual packet processing, and then I will talk to that.
Well, so we ended up getting faster throughput, right? But then we decided, faster is not enough. Let's get more greedy, right? So we tried to get faster than faster, right? And that's exactly how it's going with the Melbourne Cup around here. So with vector, so what we came up with after DPDK, OVS DPDK is basically vector packet processing. So OVS, well, most of the DPDK technologies work scalar-based, wherein you look through every packet and then process the packet before you went to the next packet, right? But think about a mode wherein instead of going through each and every packet, if you take a subset of packets and then actually walk through them, this is what vector packet processing does. So what vector packet processing does is it divides the processes into a number of graph nodes, and then it picks up a bunch of packets. And basically, if you see over here, a vector of packet flows through the entire graph nodes. And due to this, instead of actually looking through each and every packet, you're looking through a chunk of packets. And based on this, you actually can get much reliable and faster performances. So this is something that takes you a step ahead than normal DPDK vSwitches and stuff. Okay, here you go. So that's how it moves. So you see a bunch of packets are moving through different graph nodes from the input space all the way to the output. And typically because of instead of being one, it's multiple packets together, you typically end up processing larger chunks instead of doing one at a time. So with that, we come to the end of this presentation, and we would open up the floor to any questions. Yep.
So I missed the beginning, but the VPP is adopted right now in OpenStack, or
Yes. We do have a project in OpenStack called as Networking VPP, and my friend out here, Ian Wells, is actually the PTG for that. And we did, I think about an hour back, have a talk on networking VPP and stuff. So basically, you could install VPP as a vSwitch in OpenStack and use a networking VPP driver to program it.
So I have a question. So
Sure.
how does it compare to using like SmartNICs?
That's an interesting question, and I think it depends rather on the smart NICs that you're using and the integration that you're working with. But basically, VPP, if you're using it as your forwarder, you don't need to spend extra on the hardware. You don't need to choose, particularly expensive smart NICs. You can work with off-the-shelf components. So you're back to building a cloud out of the cheapest components available to do the job.
Yeah, and to add to that, with VPP, actually what you could also do is, because most of the processes are graph nodes, you could replace the hardware acceleration graph node with the SmartNIC graph node that you have. As long as it is DPDK compatible, it will stitch in into VPP. So you would have the performance from the software side as well as from the hardware side. Yeah. So VPP is the vSwitch from FDIO. So whatever we presented out here with as when we spoke about vector packet processing, is the FDIO technology that we are presenting.
Is there any plan to use VPP for containers?
So the question was if there's a plan to use VPP for containers, and the answer to that is yes, we're actually looking at that today. There's two issues with containers. One is that, again, that divide between enterprise and NFV workloads is there. And containers are very enterprise-focused at the moment. They terminate packets and they turn them into, for instance, TCP streams, which then come up through normal kernel interfaces into processes that are actually running into the containers. And there's not a great deal that VPP can do to speed that process up because a lot of the slowness is within the kernel mode of the network stack. But one of the things we've been exploring is whether you can actually turn that kernel network stack into something that runs within a process and then offer an interface to the process from the actual application that you're running, which might give us a big boost in speeds. The other one is when you're looking at NFV, whether we can do things like, for instance, linking the output of one container, the packet flow from one container, to the input of the next one, and then eventually feeding it out through an SROV NIC to the network, which is also something we're exploring at the moment.
Does it have any implication on like chaining or?
Technically, it could do. VPP's got a lot of features available in it, so when we want to, we can actually bring in some of the additional features to get some of these technologies going. For instance, NSH is one service chaining technology which is in VPP today, which already has implementations. You just need to add the control plane and the APIs from Neutron down to tell VPP what you want it to do. Okay, thank you everybody, and we'll leave you to the rest of your day.
Thank you.